Okay, here we're considering the conservation of momentum again, but this time we're looking at it in 2 dimensions. And really in 2 dimensions it's no more difficult than it was in 1 dimension, especially if we use an algebraic vector approach to solve these problems. In this lesson, really all we're going to do is use 2 examples, 2 very useful examples, which can kind of act as a guide for solving these types of problems, because I'm going to take a very similar approach in each. And you've already seen the approach that I've taken. It's no different than when we look at linear momentum in 1 dimension. Let's begin by examining some curling stones. So 2 identical curling stones, they both have a mass of 19.5 kilograms, and they collide. The first stone hits the stationary second stone. So here's the first stone right here, and it hits this guy with a velocity of 5.0 meters per second north. So this guy's traveling north, so j hat direction, and he's going to hit him. The velocity of the first stone is 3.2 meters per second north, 30 degrees west after the collision. So we know what happens to this stone. It hits and it glances off this way. We need to find the velocity of the second stone after the collision. So we're going to ignore friction, and what we're going to say is, okay, well, let's diagram out what's going to happen after. So this is the initial state. So what does the final state look like? Well, in this case, if this stone glances off to this side, even if we don't have a guess, the math will tell us what the answer is, even if we don't have a guess. But in this case, we kind of do have a guess. If this guy comes up like here and glances off in this direction, then this guy, to conserve momentum, has to glance off in this direction, right, over on this angle. So basically our final vector is going to say that, okay, well, this stone is going to glance off in this direction, and this stone is going to glance off in this direction. No problem. We know the masses of the 2 stones. They're equal, and they're 19.5 kilograms. We know V1 initial, and that's 5 j hat meters per second. We know V2 initial, and it's 0. We also know V1 final. And we can figure that out in I hat and j hat notation by simply resolving this velocity vector into its x and y components. And so that's what we're going to do. V1x final is 3.2 cos 60 in the negative I hat direction. V1y final is 3.2 sine 60 in the positive j hat direction. This is negative I hat because this little velocity vector up here, this is in the negative x direction. Okay, so this little guy right here, in our standard coordinate system, this is in the negative direction. So that's why we put the negative I hat there. Okay, let's move the page up, and let's say momentum initial equals momentum final, the standard way that we start these problems. What we get is we get m1 v1 initially plus m2 v2 initially. So this is what we have before. We already know what this velocity is, which means this term is going to cancel to 0, which is nice. We know v1 final, we can find v2 final. So let's sub in, and here's what we have. 19.5 times 5 j hat plus 0, this term disappears. 19.5, and we get negative 1.6 I hat plus 2.77 j hat plus 19.5, and this is what we're trying to find. Now, if you're savvy, you can simply say, hey, I get an M1 here, I get an M1 here, I get an M1 here, really this is M2, but they're the same thing. I could cancel them all. And yes, you could. But be very careful, because if you have different masses, you cannot do that. So this solution is not savvy, because this solution simply multiplies everything together, and that's exactly what this line represents. It represents all of these terms being multiplied out. And what we'll do now is we'll collect like terms, trying to isolate V2 final. So we're going to move this guy over to this side, we're going to move this guy over to this side. When we're collecting like terms, remember that j hats can fraternize with j hats, and I hats can fraternize with I hats, but they cannot mix. You can't mix an I hat and a j hat together. They got to stay separate, and thank goodness for that, because we have 31.2 I hat plus 43.5 j hat equals 19.5, and if we divide out the 19.5, we get our final answer, which is 1.6 I hat plus 2.23 j hat meters per second. And this actually, does this match what our prediction was in the introduction? At the very beginning, we said, oh, it's probably going to recoil off in the northwest direction. You betcha. That definitely meets what we thought it would. So let's take a look at another example now. A 5-kilogram cherry bomb at rest explodes into 3 pieces, each of which travels parallel to the ground. Okay, so this is a very big cherry bomb because it was 5 kilograms. So we're just going to pretend that it was a huge cherry bomb. The first piece has a mass of 1.2 kilograms, and it travels at 5.5 meters per second at an angle of 20 degrees south of east. The second piece has a mass of 2.5 kilograms, and it travels at 4.1 meters per second at an angle of 25 degrees north of east. Let's determine the velocity of the third piece as we go. So here's our little bomb, our little cherry bomb, and we've got 5.5, and this is of course south of the east direction, and this is 4.1, and this is 25 degrees north of the east direction. So which way is the third piece going to go to balance the momentum of these two? It's going to shoot out in this way. Okay, it has to. We got to have something to balance these x momentums. So how do we do this? Well, let's talk about M1. M1 is 1.2 kilograms. We can talk about M2. It's 2.5 kilograms. M3, by deduction, we can calculate because we knew the total mass of the bomb at the beginning. And so this cherry bomb was 5 kilograms minus 1 fragment minus the second fragment gives us the mass of the third fragment. And it's 1.3 kilograms. Momentum initially is equal to 0. Why? Because it was initially at rest. And so this is nice because this is going to ease our calculations. We can now take these two velocity vectors and resolve them into their x and y components. So here's the first velocity, v1, and this is the 5.5. And we get 5.5 cos 20 I hat minus 5.5 sine 20 j hat. We've got v2, and its x is 4.1 cos 25 I hat, and its v2y is 4.1 sine 25 j hat. So there it is. Everything set up and ready to go. Momentum initial equals momentum final. Are you starting to see a pattern with how we solve these? Because it's basically a similar thing over and over again. Here we know the momentum initial, and it was 0. And what we have in the end is M1 V1 final plus M2 V2 final plus M3 V3 final. We have, when we make our substitutions, these values. Okay, so this is just subbing things in. Now in the next step, hopefully this isn't too much for you, but in the next step, I'm going to distribute mass through here. I'm going to distribute mass through here. I'm going to collect like terms on this side, and I'm going to move those like terms over. And there it is. Okay, so I've collected all my I hat like terms and added them. I've collected all of my j hat like terms and I've added them, and I've moved them over to the other side, and I'm about to divide by 1.3. So here I go, and when I do that, I get minus 11.93 I hat, minus 1.59 j hat meters per second, and I can round my answer off, and I can say that V final is equal to minus 11 I hat minus 1.6 j hat. So it's kind of in the downwards direction, but we notice that it has a lot more x velocity than it does y velocity. And it's because those two y components of the two momentums that we had were pretty balanced out. So we didn't actually need a lot here. We needed a lot here to balance out those first two pieces. That is 2 examples of momentum in the conservation of momentum in 2 dimensions. Next lesson we're on to talking about work and energy.